Hi everyone, and welcome to our week 8 lecture where we'll be covering correlations and bivariate regression. So as we've been talking about the previous couple of weeks, we've been using bivariate statistics like chi-squared tests, t-tests, ANOVA, and we are now moving into territory that will allow us to look at continuous variables. So correlation is a statistical tool that's used when you have two continuous variables, and by continuous variables I mean things like income, height, weight, expenditures, and so correlation allows us to run statistical tests on continuous variables. We're also going to start dipping our toes into bivariate regression, right? So these are essentially the ultimate tools that you'll likely be using in your final paper. So bivariate regression allows a dependent variable it must be continuous, and an independent variable. And the independent variable can be any kind of variable. It can be a nominal variable, it can be an ordinal variable, and it can be a continuous variable. So bivariate regression is one of our most flexible tools. Bivariate regression also allows us to get into more causal language because a lot of the work that we've been doing so far with chi-square tests, correlation, has more been about associations as opposed to causality. So bivariate regression really allows us to get into more causal language. So correlation coefficients. So just as an example, this is from the economic theory of voting, and it says that a better economy, right, higher GDP, lower unemployment, leads to the incumbent being more likely to get reelected. Conversely, if the economy is doing really poorly, then we would expect the incumbent would likely not get reelected. So in this case, we are going to be talking about the incumbent party vote percentage or vote share as the dependent variable, and percentage change in real GDP. And GDP here is a measure of the economy, right? Gross domestic product. And that is the independent variable. Both of these are continuous. And we are going to be looking at them. So how can we assess the relationship between those two, between incumbent party vote share and gross domestic product? We could look at a scatter plot. So here is an example. So the dependent variable, which is the incumbent party vote percentage, is along the y-axis. The dependent variable almost always goes along the y-axis, and along the x-axis is our independent variable, which is percentage change in GDP per capita. And you could perhaps say that there is a positive relationship between these two variables. You can see that it sort of moves in a positive way, but this is just me eyeballing it. We don't know for sure that this is true. This is just me looking at the data and guessing, essentially. This is where the correlation coefficient comes in, specifically the Pearson correlation coefficient, or Pearson's R. This ranges from -1 to 1. So if all of the lines in the plot line up perfectly straight with a positive slope, something like, oh, I want my pen, something like, imagine this is my plot, and all of the points go in sort of a direction like this, and all of the points, there's one, it all lines up along the line. This would have a Pearson's correlation coefficient of 1. This means that they all positively move together. Let's see if it'll let me, if all the points line up in a negative direction, like this, right, where they move in opposite directions. So as x increases, y decreases. They move in opposite directions. And all the observations lie perfectly on this line, like so. This would have a Pearson correlation coefficient of -1. If there were no relationship, if they were just like random points and there didn't seem to be any pattern there, this has a Pearson's correlation coefficient of 0, right? There essentially is no relationship between them. They don't move together at all. So here's an example. This is with a Pearson correlation coefficient of 0.37, and you can see it's sort of like a big messy cloud of data. There might be some association, but it's relatively weak. It looks like a positive one as well. So to some extent, as x increases, y also increases, but this is relatively a low correlation coefficient. Here you can see that this one is a little bit tighter though, right? The Pearson's R, or correlation coefficient, you can see that this cloud of data is a bit tighter, and this is actually quite high, 0.79. So this has these two variables, x and y, have a strong relationship of 0.79, and you can see how tightly clustered this data is. This again looks like a big cloud. This is a Pearson's correlation coefficient of about 0.25, and I wouldn't necessarily say that there's a strong relationship between x and y in this case. It sort of looks like we just threw darts at a board, and there's not necessarily a pattern. And there is somewhat of a positive relationship, but it doesn't seem to be too strong. So the way that we calculate correlation, we say this here is rho, or that's why it's also called R, Pearson's R, or rho of x and y is the covariance of x and y. So you can see here covariance is the covariance. And this is all divided by the standard deviation of x right here, and multiplied by the standard deviation of y. Now, if I ask you to calculate Pearson's R, I would likely give you the covariance of x and y, the standard deviation of x, and the standard deviation of y, just so you get a sense of how this equation works. But I don't expect you to calculate each of these together. It's actually quite a time-consuming calculation, particularly the covariance matrix. But yes, this is the underlying equation, essentially measuring how they move, how the two move together. So in our example for economic voting, we have a Pearson's correlation coefficient of 0.57. So Pearson's R, or rho, is 0.57. And this means that there's a moderately sized relationship between GDP growth and incumbent vote share. So usually when we run this in R, our results will come with a p-value to tell us whether this relationship is statistically significant or not. Chances are it is, and if our p-value falls below that 0.05 threshold, we can conclude that there is a statistically significant relationship between the economy and incumbent vote share. There we go. This brings us to regression. The issue with correlation is it doesn't really tell us the magnitude of the effect. Yes, we can say to what extent the two perhaps move together, but it doesn't really tell us when we see an increase of what happens to the dependent variable, right? When x changes, how much does y, how much would we expect it to change? And it doesn't really get at causality because it doesn't allow us to control for other things. Now at this juncture and are looking at regression, we are not going to be doing control variables just yet, but once we do, it is going to allow us to use more causal language. So our example for right now, we are interested in whether high levels of pain affect memory tasks. So we're going to ask 8 people to remember 30 objects and then ask them to recall those objects while we give them electric shocks. Now that I say it out loud, it sounds a little unethical, but I'm sure some study like this has been done. So each person is going to get a different level of shock. It will vary between 20 volts and 160 volts, and it will be in increments of 20 volts. So some people will get 40 volts, other people will get 100 volts, and one person might get 160 volts, but it will vary from person to person. And then after they've received those shocks, we'll ask them how many of those original 30 objects they remember. So in other words, for our experiment, we have two variables. The number of items recalled of those original 30, that's going to be our dependent variable, and then the level of shock. So whether they received 20, 40, 60, 80, 100, 120, 140, or 160, that is going to be our independent variable. And we're interested in how much shock they received and how much it's going to affect what they can recall. Since they are both continuous variables, we can both calculate the correlation coefficient and create a scatter plot. So, here is our scatter plot, and it looks as if there is a negative relationship, right? It seems to go down. As the voltage increases, as we move along this x-axis, the number of items that are recalled actually goes down. Okay, can I turn this pin off? There we go. Automatic. Okay. The basic idea, though, of regression is that we're going to fit a line, like I just did here, through the data. That's the best line, the line of best fit through that scatter plot. That's the underlying calculation that we'll be doing. Now, we're not necessarily going to be doing the math for regression, but that is the underlying equation and calculation. So again, here is our scatter plot from earlier. We could fit a line by eye, which is what I just did. Boop. And this line would allow us to read off a predicted value of memory given a shock level. So for instance, if I give you a shock level of 80, it looks like you would probably remember about 15 observations on average. But this is, of course, again, a line that I've done by eye. See? Oh, my hand-drawn line got really close to the PowerPoint line, right? My eye is not too bad. But what we can see here is this line, it gives us a prediction for what we would expect. But again, it's a potentially inaccurate line in some ways because I did it by eye. So we can describe a line like this with a simple equation that has two components. If you recall from algebra, y equals mx plus b, right? M in that case is the slope of the line, right? And b is the intercept of the line. So the slope, m, in our case, is how many fewer objects can a person remember as the shock is increased by 1 volt. The intercept of the line is how many objects we would expect someone to remember if they received 0 volts. So in this case, memory is y, intercept is b, m is the slope, and x is the shock. So we would expect here our intercept is the number of items that someone would be able to recall when they have received no shock. The slope is going to be how many fewer objects a person can remember as the shock is increased by 1 volt. And this here is the shock that we would administer. So 20 volts, 40 volts, 60 volts. And then this would be our expected, memory would be our expected value of like controlling for the intercept or calculating for the intercept, the slope, and the shock that we would be administering. So in this case, for the line that I drew earlier, as everything flows in, the intercept is 27. Right, from that line that I drew earlier. The intercept is 27. We calculate the slope by doing rise over run. So 10, right, it came from 10 or about that, minus 17 is -7, and 120 minus 50 is 70. And this leads to a slope. Obviously, these lines are not exactly right because I wanted them to be big enough. But in this case, for this line, we have a rise of about -7, so it decreases 7 objects when we increase by 70 voltages, right? 70 volts. So -7 over 70 equals -0.1. And this is just how we typically measure slope, rise over run. So how many units did it increase when we moved over this many, or how many did it decrease? So this leads to our equation. So we have memory, so the number of items that you would recall, equals 27, which is our intercept, plus -0.1 times the shock that I give you, 20 volts, 40 volts, 60 volts. So for every 1 volt increase in the shock, the score on the memory test is going to decrease by 0.1. So if I give you 20 volts, that will decrease your the number of items you're able to recall by 2. So if someone receives a 10 volt shock, we predict that they will score about a 26, right? So 27, which is our intercept minus 10, the number of volts that we're going to give them, times 0.1, which is our slope, equals 27 minus 1, 26 items. If someone receives a 90 volt shock, we'll predict that they're going to have a score of 18. 27 minus 27, which is again our intercept, minus 90, which is the shocks, the volts that we're going to be giving them, times 0.1, or really -0.1. And that will ultimately equal 27 minus 9 equals 18. So when we administer a 90 volt shock, we expect that the participant will remember about 18 items. So we can generalize this equation. It will look like this. Y equals alpha, which is our intercept, plus beta, which is our slope, times x. So y in this case is the dependent variable of how many items you can recall. X is the independent variable, which is how many volts you received. Alpha is the intercept, and again, beta is the slope of the line. So positive betas mean that as x increases, y increases. Negative betas mean that as x increases, y decreases, which is what we have seen in this voltage example. As you increase that voltage, in turn, how many items people will recall has declined. And if beta is 0 or close to 0, then we would conclude that there is no relationship between the two variables, which means as x increases, y does not change. So given that different people, this was just me fitting a line by eye, but perhaps if I let lots of people do this, people would come up with different lines, right? Even if it's just marginally different, perhaps these people have astigmatism, right? So we need a general way to fit a line without just relying on people's eyes, because chances are people's eyes are not completely accurate. So we use regression, and we do this by minimizing the sum of the squared deviations from the line. So that just means all of those points, we want to make sure that the line gets as close to all of them as possible, minimizing the error or differences between the point, the observation, and the line of best fit. So the line that ends up being drawn with regression is called the ordinary least squares line, because it minimizes those squares, the differences between the observations and the line of best fit. We also call this a regression line. So if I entered all of this data into R and pushed the correct buttons, I would learn that in our case, beta is -0.12, and alpha is actually 24.5. So my guess was good, but it wasn't accurate. It didn't minimize the sum of squares, but R did manage to do that. So this says that if we give someone a 100-volt shock, then we predict that they will score about a 12.5 on the test, right? We get that number because we multiply 0.12 times 100, which leads to 12 in this right here. So 24.5, which is our intercept, minus 12 would be 12.5. So because the slope is constant, it's a straight line, for every 1 volt increase in the shock, we expect the memory score to decline by 0.12. This means that there is a linear relationship between x and y. So the thing is, though, is our equation for a line, which is here, is not a perfect representation of reality, right? For every 10 volts that I increase, on average, it would likely lead to a 0.12 decrease in the number of items people can remember, but that's on average. It's not for every single person, so therefore it is not a perfect representation of reality. So a lot of people will have values that are either above or below that predicted line. Therefore, a better representation of reality is something like this. So I just represents the observation. You don't need to think too much about it right now. But y is the dependent variable. It equals alpha, which is the intercept, just as it was before, plus beta, which is our coefficient, or m, if we're going back to algebra, times x, which is our independent variable, and then here's our big addition, plus u. Plus u. This u here is our error term. This is our error term. So all those differences between the observation and the line of best fit are going to fall into this right here, this error term. So what's in the error term? Well, usually in our case, like there isn't such a thing as single causation, right? And this is why regression is so helpful. So what I mean by single causation is usually it's not just one thing that causes something, right? So going back to our example of shocks and how many objects someone can remember, some people might be better prepared. They may have more cognitive abilities to remember things. So say that the individual is younger or they've had more education, they may be better prepared to remember all of those objects, right? And so it's not just how many shocks someone is given. There are other things that might affect them. So here is an example, going back to the economic voting. Our primary theory, right, is that the economy will affect incumbent party vote share. There might be some other things too, though, like the popularity of the president is a strong one, as well as the effect of the popularity of the opposition leader. And then ultimately the error turn. So every time you add another independent variable into your model, another cause of your dependent variable, your error term, right, is going to shrink a little bit. It's going to get smaller. So every time you're able to better explain your dependent variable, that error term is going to shrink. So how do you interpret beta? This is typically the primary thing that we're going to be interpreting. So beta is called the regression coefficient. I may either call it beta or the coefficient. It is a numerical representation of the size and direction of the effect between our two variables. So as our independent variable increases by one full integer, our dependent variable will increase by beta integers. So whatever number that beta or coefficient is, that's how much our dependent variable is going to increase. So you will only need to interpret that coefficient if the p-value is less than 0.05. So if the the relationship is statistically significant. So you will only need to interpret beta in your output if that p-value that accompanies it is less than 0.05. And we'll go over this a bit in the lab. So here is a quick example to just sort of show you what it might look like. So I am interested in, say, the number of apples that someone eats per month and how that affects a person's health. And in this case, I'm looking at the number of doctor visits that someone has per month, right? With the idea that an apple a day keeps the doctor away. We would theoretically expect that the more apples someone eats, the fewer doctor's visits they'll have. And in our case, I run a regression analysis and I get a beta, or a coefficient, of -1.2 and a p-value of 0.03. So given that the p-value is 0.03, we can conclude that there is a statistically significant relationship between the number of apples eaten per month and the number of doctor's visits. So then I turn to beta, or the coefficient, and I say a 1 integer increase in our independent variable, which is apple consumption, leads to a -1.2 decrease, or a 1.2 decrease in our dependent variable. So I would write something like, the effect of apples on doctor's visits is statistically significant with a p-value of 0.03. Specifically, an increase of 1 in the number of apples eaten per month leads to an estimated decrease of 1.2 doctor visits per month. So really, for every 1 apple that someone eats on average, we would expect the number of doctor's visits to decrease by 1.2. Okay, so I would recommend now that you guys head over to the lab and we will go over some regression output and get us going there, because really this is sort of the foundation for where our final papers are headed.